So I want to talk a little bit more about how we can represent rate because we're saying it's the change in concentration over the change in time. But that's going to look really different depending on how we represent that change. So we have a few different ways of representing rate that I want to introduce. So first is average rate. That's the rate during a specific interval of time, and it assumes a linear change in concentration, which means that it'll have the same rate of change over that entire time period. Or it would be this red line here on the screen. So that's not really how reaction dynamics work. So at first, the rate is actually very fast compared to later because you have more reactants that are colliding. With more reactants colliding, you're going to have more products form. But over time, as that concentration of reactants decreases, well, there's less collisions between reactants because there's fewer of them around. And so your reaction rate decreases. And so don't see a linear like change in concentration. Instead, you see this like curvy kind right here where it slows down over time. So a linear average rate is going to be an approximation. And it's where you take 2 points on your line. Right here, we're doing this point here and this point here, and you subtract them, and you basically get the slope of that line, the rise over the run. And so you see what's the concentration of the reactant at one time minus the concentration of the reactant at another time, and then divide that by the amount of time that passed between those two measurements. And that gives you the average rate. This is negative because we're looking at reactants, we're looking at that rate decrease. So this is one way to measure it. And now let's look at the instantaneous rate of a reaction. This is the rate of the reaction at a specific time in the reaction. And it's equivalent to the slope of the line that's actually tangent to the curve that represents how the rate of the reaction is changing with concentration and time. And so here, when we have our reaction rate change with time, we still have that kind of nice slope where it has a faster rate in the beginning and a slower rate at the end. And we're going to pinpoint the reaction rate at a specific time. So here we're looking at 50 seconds. And so we're really looking at these points here on so the first one is at 50 seconds, and it looks like the concentration is between about 0.2 and zero point 0.4. And so we draw a line here tangent to that slope or to that point, and we find the slope of that line, that tangent line. And so in this case, looking at the rate for the reactants decreasing, we would see a negative 0.28 divided by 40 seconds, or 0.007 molarity per second. And that's taking then the information from that tangent line, the slope of it, looking at a change in time versus a change in our Y value, which is our concentration. And you can do that for both the reactants decreasing. You can also do it for the products increasing, which is right here. Here's that tangent line to this point at 50 seconds. And so this is a great way of knowing, like, at this point in the reaction, here is the rate that the reaction is going at. But you really need to specify at what time you're looking at that. Is it in the beginning of the reaction, towards the end? Because that rate of the reaction is going to be changing throughout the entire reaction. And it's important to note that at that 50 seconds, the rate that I'll calculate for that tangent line for the rate of the products increasing or the rate of the reactants decreasing will be the same value if I'm looking at the exact same time. So that change in the rate of the reaction will change the same for reactants and products as I look at different intervals of time throughout my reaction. All right, so, and here to show you that, here's the other one. So we're looking at this point right here. We just calculated a 0.007 molarity per second for our products or our reactants decreasing. Now looking at the line tangent to the 50-second rate point for our products increasing in concentration, we can calculate the slope of the line tangent. We'll use this point here and here. So we're looking at 40 seconds for our change in time and 0.56 molarity for our change in concentration. And remember, we're now dividing also by 1/2 because we have a 2 coefficient. And so we put in the rate information from our graph over here. And we calculate a value that is in fact the same. It's 0.007 molarity per second. So we'll be able to get this same rate no matter which reactant or product we're tracking, as long as we're doing it at that 50-second marker. All right, but now I'd like to talk about the type of rate that we're going to use the most in this class, and that is the initial rate of the reaction. And so this is one of our average rates. It's not an instantaneous rate, and it's an average rate between our first two data points that we would collect in a lab. So if I'm actually going to be studying one of these reactions, I am going to be measuring the concentration of a reactant or product at intervals of time. And I'm going to do that until I think the reaction is basically done, and then I can plot it and calculate my rates. And I might want to know the instantaneous rate at a specific time, but for comparison to other reactants or products in the reaction, and to compare between whatever reaction I'm studying and another one, or the same reaction under different conditions, I need to have a consistent way of measuring rate and comparing them across different trials. And so for this, we use initial rates. Initial rates are the average rate between the first two data points, as I said. So you always have your first one is going to be at time 0. And then it's your first data point, your first concentration that you measure. And so you're really just looking at those first two things, how quickly the reaction starts. And this will be the fastest rate of the reaction because it's going to slow down as we form products and we decrease the concentration of our reactants, limiting their opportunities to collide and form products. So we'll just take the first two data point average. And so when we do it for this one, we see that we get a concentration that is 4.76 times 10 to the negative fifth for this concentration of phosphorus increasing over time. We'll still apply the coefficients that we know about if we need to, or the negative value for reactant. Oh, sorry, this was a reactant decreasing. We've got a negative sign here. But we're just going to be looking at those first two data points. And so that's why, and so what this comes down to when you're in the lab, the way this translates is that if you're doing a kinetics experiment, it is extremely important to start your timer at the exact moment that you're combining your reactants, and lining up those two events is critical to getting accurate data for that first data point measurement of concentration. So there's a lot of ways that we report rate, or we explore what the rate of a reaction is experimentally. And we're really looking for a way of measuring how concentration changes. We can do that as long as we have something that's what I called like a spectroscopic marker, right? Something that we can measure about a reactant or a product. And so some of the methods that are used are polarimetry, spectroscopy, measuring the pressure of a system if we have a gas increasing or decreasing with the reaction. Gas chromatography can be used. You take little samples and then learn what the composition is relative of the different compounds. But you have to like take a little sample, do a test, take a little sample, do a test. Nuclear magnetic resonance, which is called NMR, which is looking at the way electrons are spinning in the compound, and you can use it to identify different reactants or products in your reaction and see how the signals decrease or increase as their concentrations increase or decrease. Cyclic voltammetry, which is measuring reduction potentials. So there's lots of ways. Here's an example. So here's an example with spectroscopy where you're measuring the light that's being absorbed by your compound over a range of wavelengths. And so this will give a characteristic signature for a colored compound. And so we have something that's kind of reddish colored that's right here that we start with initially. So it's this one right here with this peak at 452, and that's at time 0. So then as time passes, we see that this decreases and a new peak increases at 565, and we see the color slowly change from this kind of reddish color to this bluish color um, over time. And you can see that we see this rate of change is really fast in the beginning, and it really slows down towards the end of measuring this reaction. And so in this first one, we have a 2-minute time difference between our initial and our first data point. And so if we were measuring that initial rate, we would take that change in concentration and divide it by the 2 minutes. And so here what we're doing is we're taking scans of how the compounds absorb light every 2 minutes, right? And so you're taking it at regular intervals of time and seeing how the concentration changes, but as measured by a change in absorbance decreasing if the compound's decreasing. And so these are the kinds of ways that we actually explore this in the lab. And this is actually straight out of like an old lab I worked for and how we were measuring the kinetics of a reaction. And so this is kind of a common methodology.